So far, we've explored combinational circuits exclusively. Most systems use combinational circuits, but also include storage elements. Having storage elements, we need to describe them using sequential circuits. This presentation looks at an overview of sequential circuits and covers terms and definitions, including key concepts such as storage and synchronous operation. Here we can see a block diagram of a sequential circuit that includes the combinational circuit and storage elements. The information in the elements at a given point in time defines the state of the sequential circuit at that time. Outputs in a sequential circuit are a function of the inputs and the present state of its storage elements. Likewise, the next state of the storage elements relies on inputs in the present state. So we specify a sequential circuit by a time sequence of inputs, internal states, and outputs. There are two main types of sequential circuits. Their classification depends on the times at which their inputs are observed and their internal state changes. We can define synchronous sequential circuits based on the knowledge of its signals at discrete instances of time. In contrast, asynchronous sequential circuits depend on the inputs at any instant of time and the order and continuous time in which the inputs change. Information is stored in digital systems in many ways, including the use of logic circuits. This figure shows a buffer. The buffer has the gate delay of t sub g. Since information present in the buffer input at time t appears at the buffer output at time t plus t sub g, we technically stored the information for t sub g time units before it gets lost. However, we usually want to store information for a bit longer. Imagine that we connect the output of the buffer back to its input in the same way that UH-Hilo feeds mulch back to the tree from which it came. In these figures, both 0 and 1 are stored indefinitely. As we saw on the last slide, storage can be constructed from logic with delay connections in a closed loop. Any loop that produces such storage must have no inversion of the signal around the loop, so we can implement a buffer using two inverters as shown here. Sadly, there is no way for the information to be changed without providing additional inputs to override these stored values. If we replace the inverters with NOR and NAND gates, the information can be changed. Asynchronous storage circuits called latches are made in this manner. Complex asynchronous circuits are difficult to design since their behavior is highly dependent on the delay of the gates and the timing of the input changes. As a result, most designers choose to go with synchronous models for circuits. However, some asynchronous design is necessary. We use asynchronous latches as blocks to build flip-flops, and these are used to store information in synchronous circuits. A synchronous sequential circuit employs signals that affect the storage elements only at discrete instances of time. We use a clock generator which produces a periodic train of clock pulses that get distributed throughout the system. The outputs of storage elements can change their value only in the presence of clock pulses. Synchronous sequential circuits that use clock pulses as inputs for storage elements are called clock sequential circuits. They operate correctly in spite of wide differences in circuit delays and are relatively easy to design. The storage elements used in the simplest form of clock sequential circuits are called flip-flops. For simplicity, we assume that the circuits have a single clock signal. A flip-flop is a binary storage device capable of storing one bit of information. Here we see a block diagram of a synchronous clock sequential circuit. The flip-flops receive their inputs from the combinational circuit and also from a clock signal with pulses that occur at fixed intervals of time. You can see these pulses in the timing diagram below it. The flip-flops can change state only in the response to a clock pulse. When a clock pulse is absent, the flip-flop outputs cannot change even if the outputs of the combinational circuit driving their inputs change in value. Thus, the feedback loop between the combinational logic and the flip-flops are broken. As a result, a transition from one state to the other occurs only at fixed time intervals dictated by the clock pulses. The sequential circuit outputs are shown as outputs of the combinational circuit. This is valid even when some sequential circuit outputs are actually the flip-flop outputs. So we talked quite a bit about flip-flops. A flip-flop has one or two outputs, one for the normal value of the bit stored and an optional one for the complemented value of the bit stored. Binary information can enter a flip-flop in a variety of ways, a fact that gives rise to different types of flip-flops that we'll see later in this module. We'll talk a lot about D flip-flops, but there are others such as JK and T flip-flops. To get ready for flip-flops, we'll take a look at something called latches in the next presentation. Thanks as always for watching. Be sure to check La Lima, and as stated previously, we'll cover latches in the next presentation.